I think it's right, yeah. No, but I'm confused. Okay. But I'm confused now. Sorry? I think it's minus t, yes.
Yeah, you look for QT at a minimum, so it should be minus 2 there.
Yes. Yes, yes.
And you demand that QB has only positive eigenvalues. And then this minus t is correct. Because
So at large t, you can ignore this guy and just do the classical physics of this guy.
yeah, that's just part of the other thing which gets evaluated at the saddle point. Everything else gets evaluated at the saddle point, and the one loop determinant comes only from QB. That's the issue.
But det skulle jag bara man kan stänga det. Och bara man kan stänga. You are derivative. You are considering derivative by exponential minus t QB, so there should be over minus.
Ah, okay, yes. Yes, okay. That doesn't matter, yes. Of all the messes I'm making, this is the least. Okay. Yeah, so that's non-trivial. So this argument looks very slick, and it sounds like you will always be able to do this. But it's a non-trivial fact that whether you can construct such a B. Let me tell you a B that if you can make it work, is kind of canonical. What you can take is V. So V, of course, is fermionic, because QB contains bosonic terms. So what you can do is you can do the sum over all the fermions in the theory of the variation of the fermions dagger times the fermion. Okay? Now, if you're able to define a suitable notion of dagger, and now you compute the bosonic part of QB, you get something like that, right? So this will satisfy all the criteria, but it's not guaranteed that you're able to define a suitable notion of conjugation such that this guy will satisfy all the properties. But this, if you wish, this would be the canonical naive guess of what B would be in general. But of course, you can use different Bs. In fact, the thing I want to say is that in this argument, there are several choices we made. There was a choice of Q, but there was also a choice of B. And you can exploit this to, for example, by using different choices of Bs. It can happen that the saddle points associated to the two deformations are different. And then even though the path integral, of course, is the same in both deformations, but it looks different. So you would have an equality of the partition function computed with one deformation term, giving you can represent the partition function in two completely different ways, okay? Where you integrate over completely different space of saddle points. Okay? And this is actually what happens for the case of the two-sphere. It turns out, and it's very useful, that you can choose two different deformation terms, that in one case, the space of saddle points are completely different. And having an answer written in two different ways gives you insight. Actually, that's how you get an insight of what is the physics of these sphere partition functions. Okay. The same okay, so now let me say a few quick things. So the same logic that I use here to kind of argue for this localization argument can also be used to prove the coupling theorems. Okay? So one thing that you can try to do is consider coupling. So lambda is a coupling in your theory that multiplies a certain operator. Okay? By the same argument, I hope it will be clear, if the operator O, so this lambda can be several things. It can be a Gates coupling, a Yukawa coupling, whatever. Now, imagine that O can be written as Q of some other operator, O prime. okay? Then essentially by an identical argument, what you can prove is that the partition function will be independent of lambda, okay? So if the operator is Q exact, this implies that d lambda of Z is 0, okay? So even before you compute anything, you already know that your partition function, if you have Q exact operators that multiply couplings, will not appear in the final result. And this is very powerful because, for example, in examples where you're in dimensions less than 3, in which the gates coupling has positive mass dimension, you can show that in these examples that G square, the operator that multiplies G square is Q exact, okay? So that means that the partition function of the theory does not depend at all on G square. And now you remember that below 4 dimensions, the gate states are supernormalizable. Sorry, Gautam, to write this diagram again. I know you don't like it, but. So what you have is a theory that flows from a supernormalizable gate in the ultraviolet to some infrared theory. And now what you can do is use the fact that the partition function doesn't depend on G squared to argue that, of course, the infrared fixed point is at, formally is at the limit where G squared goes to infinity, because G has mass dimension. So what this argument shows you is that Z is a renormalization group invariant observable. So you can capture properties of the infrared fixed point by understanding the theory in the ultraviolet, which is very calculable because it's super normalizable. Okay? So this is a kind of argument that, a kind of an application of this idea that you should always try to, before doing anything, understand what parameters will your partition function depend on, because that's telling you information about what the physics of it is. Well, but if O is invariant under V, it does. But which usually, yeah. So I have to impose that O is B invariant.
Yes.
Yes.
So in addition to this being Q exact,
Mm-hmm.
it also has to be Q close because these are independent conditions.
Yes. Right. And for example, this is what happens, right? So what multiplies G squared is the vector multiplet action, which is of course Q closed, but it just happens to also be Q exact in this setup. That, by the way, this is not true in 4 dimensions. In 4 dimensions, the partition function does depend on G and Mills. Okay, so I don't have much time. I will start. So this was very kind of a general argument. I will try to now sketch how this argument can be applied to a particular example.
Sorry, so actually is Q exact in that space?
On the okay, I'm having in mind on the sphere, on the curve, on the curved manifold.
Any complex or conformally flat?
I think it's true in any supersymmetric, I think it's true, but I'm not 100% sure. I think it's true for any supersymmetric background above 4 dimensions. I think it's, but it's definitely true for the sphere. Okay, so what will be kind of a toy example of how to do this, or an application of these ideas? So what we'll do is study 2-dimensional n equals 2,2 quantum field theories. So this means that supersymmetries in 2 dimensions in Lorentzian signature, also Euclidean, supersymmetries are labeled by the number of left chiral and right chiral supercharges. So there are 4, which is the same as 4-dimensional n equals 1 supersymmetry that you know from Wesenberger. Most of the multiplets in this theory can be obtained just by dimensional reduction of the multiplets in 4D n equals 1, but there are new ones that can exist in 2 dimensions that cannot exist in higher dimensions that will play an important role. Okay? So let me just tell you a couple of very quick, because I don't have much time, reasons why one might want to study such theories. One of them is that they share many of the dynamical features of Yang-Mills theories in 4 dimensions. So these are theories, so such theories in 2 dimensions can exhibit mass gap, chiral symmetry breaking, they have instantons. Okay? So these are kind of rich theories. And the other one is that they play an important role in string theory. So what is string theory? At some point in string theory, there was something called strings, which are described by a world sheet. It's a 2-dimensional Riemann surface, sigma, that describes embedding on some space-time X, which we call the target space. This is the world sheet. And in some sense, the classical equations of motion of string theory is the statement that the theory that lives in this world sheet is a 2-dimensional with some extra conditions. It's an n equals 2,2 superconformal field theory. Okay? So one of the things that this is useful for is also using this idea that things don't depend on the RG scale. Studying these theories gives you access to the world sheet theory of a string propagating on some target space, in particular, Calabi-Yau manifolds, which were originally arrived at because they have some, the effective field theories that you get by studying them have some interesting phenomenological features, okay? And then in this picture of string theory, of course, I should give a course on string theory, but I can't. All the features, all the correlators on the world sheet have a direct space-time interpretation. Okay? So by computing something on the world sheet, you learn something about space-time. Okay? And we will see one particular example of that. Okay? So these are just 2 quick motivations why you'd want to study these 2-dimensional theories. Okay. So now let's follow the recipes that I mentioned of how to construct these theories when I want to study the theory on the 2-sphere, on the round 2-sphere for now. So let's put on a 2-sphere, okay? It turns out that there are 2 different ways of putting a flat space Poincare 2,2 invariant theory on the 2-sphere. And the way you should think about this from the logic, the first logic of how to put supersymmetry on a sphere is the following. You start with a 2-dimensional n equals 2,2 superconformal algebra, okay? And then you demand, of course, this has superconformal generators that are which are conformal generators on the sphere. And you look for subalgebras of this guy that close into the isometries of the 2-sphere, okay, which is SU2. It turns out that there are 2 different inequivalent ways of doing it that give you 2 different supersymmetry algebras, 2 different sets of SUSY transformations, and 2 different Lagrangians. So let's call this SU21/A, SU2/1B. Okay? So once you decide that you want to study the theory on the 2-sphere, you have to decide whether you're going to put it on the sphere while preserving this or preserving that. Okay? It turns out that a given theory can be put in either way, and the partition function computed in this theory and this theory computes different things. Okay? Yeah, I'm sorry, I keep forgetting that. Is this big enough? If I forget, remind me, please. So here we'll define a partition function ZA, and here a partition function ZB. Okay? I may not write this in detail, but okay, maybe just so that it doesn't look so mysterious. remember that I said that the supersymmetry on the sphere is obtained by looking at a subset of the conformal killing spinors of the superconformal algebra. So you may ask, what is the difference between the killing spinors here and the killing spinors there? So let me just write it. So for SU2 is line 1A. The spinors that generate the superisometry satisfy this equation, where R is the radius of the sphere. So this is for SU2A. And if you wish, you can think of epsilon. Epsilon is a Dirac spinor. So it's the sum of epsilon plus plus epsilon minus. The same thing with epsilon bar. So for SU2 1/B, it's a different linear combination of supercharges that generate this supersymmetry algebra. So let me define this. So let me write it and then I'll explain. Where epsilon tilde is a different combination. It's epsilon plus plus epsilon minus bar, and epsilon bar tilde is epsilon bar plus plus epsilon minus. Okay? So these are two unequivalent embeddings of the superisometry inside the conformal algebra. So this defines two different theories. If you know anything about n equals 2, 2 superconformal field theories, the R symmetry is U1A times U1B. So it's a product of two U1s, one in which one which is non-chiral and the other one which is chiral. And in this guy, U1B is preserved and U1A is projected out, while in this one is the other way around. U1B is projected out and U1A is preserved. Okay? Good. And as I said, the physics of these two partition functions is rather different. Sorry? Sorry. No, these are Dirac spinors. So epsilon is a Dirac spinor, and epsilon plus and epsilon minus are chiral spinors. In Euclidean supersymmetry, Majorana is out of the window. You should always complexify. Okay, so one thing I should have said is that in Euclidean supersymmetry, the usual reality conditions that you are accustomed for are not valid anymore, because the reality property depends on the signature of spacetime. So for example, something that you will be familiar with, in 4 dimensions, in Lorentzian signature, if you complex conjugate a spinor of left chirality, you get a right chiral spinor. That's not true in Euclidean signature. Okay? Just because there are some eyes in the generators. No. Okay, so no. So what will happen is that fix a Calabi-Yau. Okay, so this might be advanced, but let me just say quickly. So you have a Calabi-Yau, and there are two types of moduli associated to the Calabi-Yau, right? There are moduli associated. So the moduli have to do with massless fields in space-time, which from the point of view of the two-dimensional worldsheet. Okay, so let me say maybe a small parenthesis here. So exactly marginal operators. So these are operators that have dimension 1, 1. In string theory, that's the basics of string theory, have to do with massless fields in spacetime. Okay? If you study 2,2 superconformal field theory, there are two classes of exactly marginal operators that you can construct. Okay? So there are ones that are descendants, supersymmetry descendants of that come what's called the chiral ring and twisted chiral ring. Okay? And essentially the partition function ZA computes the Keller potential for the moduli associated to the chiral, okay, to the twisted chiral ring, and ZB computes the Keller potential associated to the chiral ring. Okay, So now, just for concreteness, let me focus on this, SU21/A. And so that this, and I'll write more explicitly what this thing is in case you're not very familiar with supergroups. This is just the statement that you have a supersymmetry algebra that contains an SU2 and a U1 R symmetry, and the charges are transformed in the bifundamental representation of SU2 times U1. So the interesting anti-commutator in this algebra is this. So you have two supercharges that anti-commute. Let me write it and I'll explain. So, where Jm are the SU2 isometries of S2. That's what we wanted to do, right? We wanted to find supercharges that close into some isometries. And R is the U1 vector R symmetry. Okay? Notice that if I put factors of R properly and I take the flat space limit, R to infinity, R is the radius, little r, R is the radius of the sphere, here, you will get the super Poincare algebra. Okay? I'll leave it an exercise to maybe perform contraction by taking R to infinity of 2,2 Poincare. Okay? Sorry? Okay, okay. Okay, so I will not have time to do the gauge theory. What I'll do is the simplest example of a field theory you can construct in this setup, which is already quite interesting, and which the answer is incredibly simple and elegant. And essentially because the one loop determinants will be very simple. Well, they will be trivial, essentially. So let's consider the following theory. Okay, but I'll have to tell you something quickly. Okay, so. So now that we know what the algebra is, we have to talk what are the supersymmetry multiplets. So the basic multiplets will be the ones that, as I said, come from dimensional reduction from 4d n = 1. So you'll have a vector multiplet. You'll have a chiral multiplet. Remember that in superspace language, this would be something like this. Something that's annihilated by the d-bar derivatives. Now, the thing that's very interesting, and it has to do with what I just erased, with the fact that in 2 dimensions you have 2 different types of operators, is the fact that in 2 dimensions you can define what's called a twisted chiral multiplet. This multiplet only exists in 2 dimensions because essentially Lorentz transformations in 2 dimensions do not mix left and right movers. So what you can do is define a multiplet where the derivative that annihilates the superfield is different on the left and on the right. Okay? So this is an inequivalent representation of the supersymmetry algebra. And just to connect with what I was saying before, this will be associated to chiral ring operators. And this will be associated to twisted chiral ring operators. Okay? So, as you know, these theories, let's focus just on the matter part. In usual 4d n = 1 supersymmetry, you have a superpotential that can depend on certain parameters z and the chiral multiplets phi. Okay? So this is the superpotential. And these z's are coupling constants of the theory that can be thought of as background chiral multiplets. Okay? Something that is very useful always is to promote all your coupling constants in your supersymmetric theory to be some bottom component of some super multiplet. Okay? So it's clear that since this appears in the superpotential, this guy is a chiral multiplet. It's the bottom component of a chiral multiplet. But in 2 dimensions, you can also have a twisted superpotential. Okay? And now, again, this guy will be a background twisted chiral multiplet. And these two guys are supersymmetric invariants. I mean, one way to think about it is that in 2 dimensions, you can define 2 half superspace integrals, these, or some other version which involves theta bar plus and theta minus. Okay? These 2 guys are both supersymmetric. Okay? So now let's consider very quickly just a theory of twisted chiral multiplets with a twisted superpotential, and write down what the answer for the partition function is. Okay. So such theories are called Landau-Ginzburg models. This is a generalization of the old Landau-Ginzburg models that appear when you study critical phenomena in statistical mechanics. So these are models that have a certain potential that by tuning the parameters in the potential, you can get different non-trivial fixed points in the infrared. Okay? There are supersymmetric generalizations, and this is an example of that. For example, if you take the twisted potential to be a homogeneous function yk over 2, this guy describes what's called a minimal model, the case minimal modeling of 2, 2. Okay? So this is an example in the supersymmetric context of a Landau-Ginzburg model that describes a non-trivial superconformal field theory in the infrared. Okay? The thing that's very simple about this case is that if I write the kinetic terms of this theory, I will write it. The Lagrangian on the sphere is exactly the same for the kinetic terms as it was in flat space, because essentially this action is conformal invariant, so putting on the sphere is trivial. Okay? But the superpotential term is non-trivial. It has a non-trivial 1 over R correction. Let me just write it. So G is the auxiliary field associated, is the top component of the twisted chiral multiplet. I'm almost done. And there is an important 1 over R correction to the Lagrangian that you would have in flat space. So this guy is not in flat space. In fact, if I take R to infinity, it disappears. But if you put it on the sphere, you have to have this extra term. And the thing that's very easy about this Lagrangian is that, first of all, you can very easily show that this Lagrangian is Q exact. And it's clearly written as a sum of positive definite terms. So the saddle points are just y equals constant, okay? And g equals 0. The thing that's also quite easy to show is that the one loop determinant. So you can use this guy, since this guy is Q exact by itself, you can use the action itself as a Q exact deformation. And that one loop determinant around that saddle point does not depend on y naught, okay? So the localization, the exact partition function of the two-sphere for such a model would be just the integral over the constant mode of your fields y naught. The evaluation of the action on the saddle points, so the only term that will matter will be this term. Okay? So you have reduced the full, sorry? Oh, yes. You have reduced the full functional integral of this theory to just an integral of something that is just a phase. Okay? And the thing that's remarkable is that this integral, when you consider a Landau-Ginzburg model that describes certain Calabi-Yau compactifications, computes exactly some object that is of geometrical importance in Calabi-Yau compactifications, which is the volume form on the complex structure moduli space. So this is the simplest example of how something that would be very complicated and it has an interesting geometric interpretation reduces to an essentially elementary integral that you can just do. Okay? So I should really stop. I'm sorry I ran over time. Sorry? So in order for to do that, so not this guy. So I can construct a superpotential that would describe a Calabi-Yau. But not this one. This just describes a particular minimal model at level k. But by choosing a particular superpotential, total-like superpotential, this would describe a Calabi-Yau. So this would compute the period, what's called the periods of a Calabi-Yau, or the, yeah. Maybe you can ask me in the next lecture, but by a suitable choice of W tilde, this would describe a Calabi-Yau, but it need not describe a Calabi-Yau. I mean, in particular, it can describe some other thing like a minimal model. Sorry? No. Well, one reason there is 1 over R squared is that a conformally coupled scalar in 2 dimensions, if you remember, the coefficient of R phi square is 0 in 2 dimensions. That's one of the reasons. That's why it's absolutely trivial to put this particular theory on the 2-sphere. Tomorrow, when we describe gauge theories, there is much more subtle, because obviously gauge theories in 2 dimensions are not conformal, and putting on the sphere is a bit more subtle. But very doable, of course. No, yes. So this guy would have central charge 3k, k plus 2. So the full functional integral over fields on S2 reduces to just a zero mode, the zero mode of the field y, the constant part of y. And this is just a finite dimensional integral, just an integral over the constant part of y. Well, what I said, the thing I didn't show, but it's actually a simple exercise for you to do, is to prove that this guy can be written as QB. So I can use the action itself as the regulating term. So all that I have to do is study the saddle points of this guy, which is absolutely trivial to do, because it's a sum of positive definite terms. I just have to put this guy to 0, essentially. These are the solutions. 3 minutes thought will convince you that the one-loop determinant expanded around this guy is independent of y naught, and then this is the answer. All I have to do is evaluate the action on the saddle point. Yes. It's just a constant part of the mode, right? So imagine you have a y lives on a sphere. I could do Kaluza-Klein harmonics on the sphere. I just keep the zero, only the zero mode survives. That's the volume of the sphere, 4 pi r squared. Some TT star geometry. This one? Okay, this one I don't know. Well, but TT star geometry was around that time also. So, okay. I think the studies, as far as I know, so there's other papers by Chekhoty that he studies supersymmetric quantum mechanics. He reduces the problem to supersymmetric quantum mechanics and somehow gets this. This, as you saw, is an absolutely elementary way of getting it directly. Sorry? It was an observation that in some models you could get it at this. Here, I didn't have to specify anything. This is true for any model, right? Yeah. But also, the other thing that's nice is that these guys also, which maybe they had, maybe they didn't, I don't know, that this guy itself has a geometric interpretation, which we'll discuss maybe tomorrow.
So is it generally true, like the kinetic term becomes this exact thing?
No, in general, no. These are a lucky shot here. For example, it will happen that for the Yang-Mills action, it will also be Q exact. But for example, if you study any gauge theories in 4 dimensions, the Yang-Mills action is not Q exact. So you have to construct a deformation term. But it's not you can do it. Essentially, in that case, what you can do is, remember that I wrote that V, which was the sum over the fermions of the variation of the fermions. You can construct such a deformation term. What's awful in that case is that the deformation term does not preserve the isometries of the sphere, because you've selected some particular axis of symmetry. And then what happens is that when you study the one-loop fluctuations, you cannot really use spherical harmonics, because your differential operator is not SO, in that case, SO5 invariant. So you have to resort to the calculation of the one-loop determinant using index theorems, more fancy language, which is fine. While here you can do it by just stupid spherical harmonics on the 2-sphere. But it's definitely not true that you can always use the action is not always Q-exact by any chance. That's only true in topological field theories, essentially. That's the only case where it's always true. Notice also, by the way, that this guy is not Q-exact. Very importantly, the twisted potential term is not Q-exact. That's why it appears. That
You needed
only this car, yes. 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 Well, they are not in the force. Yes. Like, yeah. There can be subtleties if you are on the torus. You can have fermionic zero modes that you have to worry about. But here, there are not even fermionic zero modes. Yeah, so it means that, well, that essentially the determinant of this guy is well defined. Okay, thanks.